So quick review from where we start with energy balances to what we end up using a lot of times, and then today we're going to talk more about adiabatic reactions and equilibrium. Okay, so there's our energy balance equation. So at this point, have we assumed anything about the system?
Is equal to 0?
I haven't set it equal to 0. I haven't set Q equal to 0. Yeah. Yeah, so that's one thing that we did, right? Is we're sort of neglecting any potential energy or kinetic energy considerations of species entering or leaving the reactor. So if I install a PFR vertically, I don't have to worry about the potential energy change from the inlet to the exit of the PFR. Anything else? Yeah.
WS is like 0.
Potential energy changes are usually pretty negligible. I don't even think people really take them into account for a distillation column, except of course you do have some pumping. You know, you have to get you have pressure loss, which kind of accounts for some of that.
Shaft work is almost
It's there.
Oh.
So that's it, really. This is just straight from mass and energy balances. There's nothing in here about reactions either, right? This formula works just as well if I'm not in a reactor. Okay, and then we're going to do a couple of things. Let's go ahead and set that to 0. All right, so what have I done? Yeah.
You assume the enthalpy changes would be from the reaction. If there is a reaction, that can be modeled next.
Yeah, so that's one thing that I certainly did is now I'm explicitly including the heat of reaction. So it's probably true that this is for a reactive system. We're also assuming that we're at steady state, right? So that's a simple assumption that we often make. What else have I done, though, in order to sort of simplify what I started with? Yeah, you can think of it as a basis, but right, I changed such that instead of having a lot of initial flows and a lot of final flows, I related those to a function where I relate everything back to the flow rate of one species, this big theta, and conversion. So what chapter of the book do we use to do that, right? This is the stoichiometry part. What if I were dealing with multiple reactions occurring simultaneously? Would I want to make this transformation? No, right? Because now I've sort of defined things in terms of a single conversion. And if I have multiple conversions because I have multiple reactions, maybe that's not a good basis. It's mathematically valid, but I would have to have multiple conversion terms in here, and it's very easy to get yourself tripped up. We're not going to be dealing with multiple reactions today, fortunately, but it will come. We haven't escaped it entirely. Okay, and now the third equation that we'll write down has, again, more assumptions built in. Yeah.
It assumes a linear change in CP as well as no phase change.
Doesn't assume a linear change in the heat capacity. Remember that these are defined based on the integral form. So, but put another way, you're either treating them as constant or you're given some representative value, right? Something that allows me to write it without the integral. And in the book, I don't think there's going to be any homeworks where they actually don't have that assumption built in. And in fact, most of the places in the book, he doesn't even use this little hat on the heat capacities. He just leaves it off with the assumption that you understand that heat capacities are actually a function of temperature, but that he's either going to give you or you are to assume that the heat capacities of the individual species are constant. Yeah?
I understand the calculation of CP hat doesn't assume that CP is linear, but since you multiply by linear combination of temperature minus temperature initial, doesn't it essentially fit it to be like linear?
If I have some confusing shape like that and I integrate under the curve, I can always relate it to some average value, but the average is not a numerical average. You can think of it like an average value, but it's not simply adding up those points and dividing by the sum. But no, I can take any integral, right, and get an area under the curve and relate that to the area of a rectangle with the same width. And that's all that this is doing. But right, no phase change. And the heat capacities are now the sort of hat variety meaning that we can just multiply it by a temperature range. What are some other common simplifications that we'll make to that energy balance? But the reason why I wanted to do this again is if you're doing homework problems or problems on a test, this is probably where you want to start. Don't start all the way back here because it'll take you, as it took us when I first put it on the board, the better part of an hour to derive this final form. This is where you want to start. And again, what have we assumed? This is valid for any flow reactor, right? Batch reactor is a little bit different because now this is not zero. But this is valid for CSTR, PFR, PBR, and no phase change in our heating streams yet.
You often also usually drop out the shaft work term.
Right, so often we assume that the shaft work is negligible. Anything else? What's that? Yeah, it's not really an assumption. You'll be told. But no, I mean, that's a good point. The adiabatic means and in fact, the problems that we're going to start with today are all adiabatic. Another one that's a bit more subtle is you might just see the initial temperatures written this way because often the inlet temperature is the same for all inlets. So certainly you can imagine like a PFR, right? If I just have one pipe, then obviously all the inlets are already getting mixed. All of my inlet components are getting mixed. But even for a CSTR, I don't know of any problems. There might be one or two in the book where you're going to say that you have two pipes going into your, dumping liquid into your CSTR, and one's coming at one temperature and one's coming at the other. I mean, you could deal with it, but often you're going to see, especially in the book, that they just kind of leave off that subscript I because they're all the same. Okay, so now for an adiabatic reaction, we can rearrange this equation to get the following. I think the other thing I'll mention is in the book, a lot of times he just puts sigma. But it's the same sigma. He just doesn't put from I equals 1 to n. So I can very easily, and again, I haven't assumed anything about the system except that it's adiabatic. This is for PFR, PBR, doesn't matter. CSTR, doesn't matter. And I can calculate the conversion as a function of the outlet temperature. Or I can calculate the outlet temperature as a function of conversion.